Alright, I'm trying out this problem called surrounded regions. Given an m cross n matrix board containing X and O, capture all regions that are four directionally surrounded by X. A region is captured by flipping all zeros or all O's into X's in that surrounded region. Let's understand the example. This is example 1. Flipping all zeros into X's in that surrounded region. Capture all regions that are four directionally surrounded by X. I did not really understand so far. So this guy, X, 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 and X below, so it's considering the region more than anything else. For this zero, there is no below, so you don't uh, eliminate this guy. But if you look at this region, on the top it's all X, on the left it's all X, on the right it's all X, on the bottom also it's X. If I look at individually for each cell, right? For this cell, X, 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 its right is 0, but that's finally there is a, and the right there is an X. Interesting. Similarly for this, there is an X, there is an X here though. Yeah, this seems to me a bit tricky. Yeah, for this guy, X, 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 and there is an X above. Hmm. So surrounding region should not be on the border, which means that only 0 on the border of the board are not flipped to X. Any 0 that is not on the border, let's call it O. Any O that is not on the border and it is not connected to an O on the border will be flipped to X. Two cells are connected if they are adjacent cells horizontally or vertically. Let's read this explanation again. Surrounded regions should not be on the border. So any 0 on the border will remain 0. That is clear. Which means that any on the border are not flipped to X. Any O that is not on the border and it is not connected to an O. And it is not connected to an O on the border will be flipped to X. Two cells are connected if the adjacent cells connected horizontally or vertically. So if you look at these all the O's, is it connected to an O on the border? No. Is it connected to an O on the border? No. Is it connected to an O? Is that it? Uh, that's interesting. Now, if this was an O, right? Then this is connected to an O on the border. Then this is connected to this. This is also connected to an O on the border. This is connected to this, which is connected to an O on the border. Yeah, that. So I'm not sure. Okay, let's see this. Let's take this input. I'll not do anything. Console. Okay, this input is given. Let's make this O. And let's see what the output comes out as. Oh, so none of them changes then. If this was an O, that would mean that all three of them are connected to this O because this is connected to this, is connected to this, and this is connected to that. Fair enough. So I'm getting some sense based on that. Can we do some sort of a connected component thing? Let's see. Really, this entire remaining X is one connected component, and this O is one connected component, and this O is another connected component. Hmm. Let's say I just simply walk through the array regularly. I see this O, I see this O is connected to this O. Then it will really depend on whether this O is connected to anything on the border. So let's just first you go through the border. Hmm. Say if I go through the border first, and this is the O I found, then is there any O that is adjacent to it? In this case, there isn't one. Let's pick up this example. Do this and let's make this guy an O. Okay. Now there is this guy. This guy has no X, so nothing to do. There is this guy. This guy is connected to this guy. So do a BFS or a DFS, basically some sort of a traversal from all the nodes, right? From all the zeros. All I want to do is get the connected components number for yeah, I think I can do that way. So from this I go left, right is nothing. This is matching. So for this I go all four directions other than the one that has been visited, and wherever I find zero, I go there. Yeah, so I do that. So I do, and that how much time will it take? It will everything will be linear. You don't traverse any node more than once, right? So number of it will be O of number of nodes. Yeah, and then we generate that number, and yeah, so okay, so let's try that out. Uh, so basically what I'm saying is this, I connect all of these together, and because they're all connected to a boundary node, they cannot be. So I'll call this, right? Let's call component number or something. Um, okay, Boolean array connected to what do you call it? Connected to the O, connected to boundary O, right? Connected to border O. If this is connected to border O, and we are only interested in all the O's, right? If this O is connected to border O, then new boolean to board dot length and board of 0 dot length. Okay, let's get more space. Now what do we do? Only we just have to walk through just the borders. So I first go through this row, then I go through this row, then this one, then I walk through this column. When I do BFS traversal. So I want to mark something called as visited. Okay, so it's Boolean array. That's fine. And now I want to do it 4 times, right? So, yeah, how do just traverse only the boundary? Maybe just 4 different loops. It's okay. Doesn't matter. Uh, all right then. I equals to that is actually is j, right? For j equals to uh, 0, j is less the number of columns. Uh, board of 0 dot length plus plus. Let's do BFS on. Uh, so we pass a specific element. Oh, we only do BFS if board of ij equals to oh, not I here. I is 0. When you do BFS, um, okay, fine. Just call it BFS and pass ij. So BFS needs board. BFS needs connected to this guy, visited, and the index. So index is 0, j. Okay, this is where I start my BFS. Similarly, uh, we also check this for the last guy. Last guy would be board dot length -1, and we'll call here board dot length -1. And this also needs to be done for the these two columns. So I equals to 0, I is less than board dot length I plus plus. If column 0 is 0, oh, then you do this and I comma 0, and here it would be row and column is the last one, which is and same would be passed here. Okay, so we do this traversal. now what? Okay, we write the BFS code, but after that, essentially, what we have to do is we have to walk through all the inner elements. So I'm avoiding the first and the last row. Similarly, in the columns as well, j equals to 1, j is less than port 0 dot length minus 1, because even the last one is not, and j plus plus. And if now we'll use this guy, if it is indeed connected to border. Firstly, we want to check if it's if board of ij is an O and it is not connected to a border O, then we change it to X. So this is linear. Everything else, everything so far is an O of number of nodes, right? Which is whatever this O of m cross n. So this is fine. Now let's write this BFS. What are we passing to BFS board? Okay, so let's take all of these. You have your board. You have your connected. You have your visited. And first things first, if it is okay, so we also need ing, yeah. Okay, so first things first is this ing if is out of border. So if I less than 0, j is less than 0, or else I is greater than equals to put length, then we know nothing to do. And if this guy is already visited, then also nothing to do. Else we mark it visited. Well, another thing which is if it is X, then we don't really care. And now we mark so the amino it's true. So this visited is true, and uh, mark this as true. And what you do, you go in the 4 different directions. That is all. So I plus 1j, I j plus 1, I j minus 1, I minus 1j, right? So that's my approach. Let's review what we did. So basically, this explanation in the example was helpful. If there is any O which is connected to an O on the boundary directly or then indirectly through, like if let's say this was an O, not this, let's say this was an O, then all of this four O's would have been ultimately connected to this boundary O, right? So we have to figure out these connected components. If these O's, for example, in this current case, these O's are not connected to any O on the boundary, so they will be connected to X. So what we're doing is we are walking through all the edges, and all the O's in the edges. We are doing a BFS from there and looking for any O's. And if we find any O's through while doing that BFS, we break the BFS as soon as we find an X, right? So for example, this O there is nothing to do, but for this O, for example, when we go in different directions, this is an O, so this is connected, this becomes connected, and from there we go to different directions. So all this a flipped T, right? They will all be considered connected to a boundary O, which is what we're trying to do. And of course, we don't visit multiple nodes again and again. We use this visited, and in the BFS, that's all we're doing. Uh, if we find an O in the BFS path, we mark it connected, mark it visited as well, so we don't visit the same nodes again and again. And we go in the four different directions. We take as soon as we fall out of the grid, we handle the edge case here. Yeah, these are the four edges from where we're doing the BFS. And finally, we go through the inner nodes and we check those inner nodes. If they are O and they are not connected to the border, then we convert them to X. Let's run code and see what happens. Fix the compilation errors. All right. So first one is accepted. Let's do run example test cases. Okay, let's take that example that we were considering. So this one, but oh, okay, this is the one that has been run. Okay, good. So yeah, so the case that we were thinking of has also worked, as well as all the test cases. Let's submit, and it works. All right, so that is the solution.